they have a quota of 250 students. They have to work with their...
Tell you a little bit about the context, and then we'll let Karen take over. The Carnegie Foundation had a new president back in something like 2004, and the vision for that president was really to do something that would impact the field of teaching in a very, very real, substantial way. So in order to do that, he really was looking for a high leverage problem, which he could begin to marshal all the forces of the Carnegie Foundation, academic research, and practitioners to solve that problem. And the one that he really identified was the community college developmental math problem and the lack of success of its students, something that I know that you know well. And so some of you may have seen other sessions that we've been doing here. We are a partner with Achieving the Dream, and so we've developed pathways, StatWay and QuantWay, which are mathematical pathways taking developmental math students to and through a college-level course in one academic year or less. In doing that, we really thought that we needed to develop curriculum and pedagogy that would have much better, stronger learning outcomes than we've experienced in the past. My own experience, I was a community college president for 12 years. I was in community colleges for 36 years and actually had retired in 2006. And what pulled me out of retirement was really looking at the work that the Carnegie Foundation was about to embark on. And in doing that work and in beginning that work, the first thing that the foundation wanted to do was to develop a set of design principles that would make sense and really engage students and also give us an opportunity to really understand how students learn. So we looked to the work of Jim Stigler, Karen Given, and their associates at UCLA, where there has been an incredible amount of activity going on, and Karen, I'm sure, will share a little bit about that with you today. If you want to really see what Jim Stigler looks like, you're welcome to come to the Carnegie Foundation for the Advancement of Teaching website, and we do have a video of Jim on there, but I know Karen will be more than able to provide the information and the findings that she and Jim have worked so hard in developing. So the work that they have has fed directly into what we call the design principles for the curriculum and the content and the pedagogy for the two pathways, for which we have now finished one full year of implementation and have had incredible success. For example, it's a 6% national average that 6% of our developmental math students get through a college-level course in a year, and our number is like 49%. So this is a pretty big jump, and we really do attribute a lot of it to some of the design of the work and the pedagogy related to it. So with that, I'd like to introduce Karen Given, and she says that she'll take questions as she goes along in her presentation. So Karen, thank you.
Great, thanks Bernadine. And that seems loud to me, is that, oh, really? Okay, okay. That's not how loud it is in my classroom, so that's feels a little loud. Anyway, thank you for coming today. My goal today is to introduce you to some of the work that we've done and share with you why I think it's important, and in fact, particularly important to the work that's going on in community colleges. So, yes, today we're talking about teaching and community college teaching. The reform efforts, and there are many going on in community college classrooms across the country, focus on a number of things. They might focus on study skills, time management, motivational orientation, helping support students in coping with their out-of-school demands with work and family, and trying to combine that with advancing their education. They also address sometimes bureaucratic barriers and trying to eliminate those. There are also efforts like the StatWay and QuantWay initiatives that are meant to redesign curriculum, sometimes to make it slower, sometimes to make it faster, sometimes to change the learning objectives. There are also efforts, reform efforts to modify supplemental instruction. So there we're getting at instruction a little bit, but we're still talking about in settings outside of the regular classroom. So what's not on that list, and what there hasn't been a great deal of research on, is regular classroom teaching in community college classrooms. So that's what we're going to be talking about today. The first thing I want to say is something about this idea that teaching as a cultural activity. So you saw culture in the title of today's talk. That comes from Jim Stigler's and together with James Hebert, their early work that resulted out of the TIMS 95 video study. So they spoke to this notion of cultural scripts, these generalized knowledge held by participants, and the mental models of those patterns of behavior. So cultural scripts are things that they guide our behavior and they guide the expectations that we have in the various settings in which we enact in our lives. Within culture, they're widely shared, and they're also very difficult to see, which is one of the reasons we like to look at classrooms across cultures. We don't see them often unless they're violated, and when they're violated, we become very aware of it. And they're also learned through observation and participation, not generally through formal study. So I'm going to take you back for a moment to, let's put you in a 4th grade English class. I'm your teacher, and I have just distributed to you a long, narrow sheet of paper. I've asked you to number from 1 to 20. What are we about to do? And I am going to say a word. What do you do? And if I stop after 5 words, what do you expect? Right. So it's been a long time since you've been in 4th grade. I'm not your English teacher. We have no prior experience together. And yet I can, with just a little bit of information, set up in you specific expectations for how you're supposed to behave and what you can expect the activity to look like. Right? All of our education is like that. There are all kinds of cultural scripts that come with our education, not just spelling tests and not just in English, but in math classrooms included, which is what we're studying. So that's what we're talking about when we're talking about teaching as a cultural activity. Those things that we know implicitly and that shared knowledge between us, even though we're strangers. Okay, so what I'd like to do today, first I want to share with you what we've learned from TIMS. I will tell you what TIMS is if you don't know. Then I'd like to share with you some of the community college work that we've done. That part was sponsored by the Carnegie Foundation, and hopefully we've brought some interesting findings back to them. And then I'll present some relevant findings from other researchers and how they're also related to what we're doing. And finally, bring it back to the idea of the implications for improving instruction. So, first thing, TIMS. TIMS is the 3rd International Math and Science Study. It's now, the T is now TRENDS, the Trends in Math and Science Study. So it's an international study done of K-12 schools in countries around the world. It's been done, well, 3rd implies it had been done twice before that. It continues past the 3rd, and that's when it was changed to TRENDS. But they study math and science achievement among students across the country, across many countries in 4th grade, 8th grade, and 12th grade. And in 1995, Jim Stigler set out to do the first video study. So to take a random sample of classrooms in a variety of, well, in 3 countries, the US, Japan, and Germany. And they collected video data in 8th grade math classrooms and studied those. And what they found was that the teaching that was going on in the Japanese classrooms was very different from what they saw in Japan, Germany and the US. And Japanese student scores are higher than student scores in Germany and the US. So lots of people naturally that led them to the conclusion that if you want to have high student scores, you need to teach as they do in Japan. Well, naturally, it's a logical conclusion from that. But based on the laughter, you know that's something we need to explore further. So in 1999, we did another video study. So it was still 3rd at the time, whatever. It was R for revisited or revised. So we did the 1999 TIMS video study. And in that one, we took a look at a broader range of countries. We did target explicitly countries with students who had high achievement scores. So the countries included Japan, Hong Kong, Australia, Switzerland, the Netherlands, the Czech Republic, and the US, just to get a wider range. And we found, in fact, that the instruction that we saw was quite different. So the question comes, why bother doing stuff like this? Well, the first is this notion of cultural scripts. If we have a hard time seeing what's going on in our own culture, one way to draw attention to it is to examine other cultures and have the people from other cultures examine us and tell us what they see. So we can see our own practices more clearly. We can also get ideas from what they're doing. So we can get ideas from the Swiss classrooms of alternatives that we might not have thought of. It stimulates discussion about choices. First, it raises the issue that there are instructional choices, things that we just take for granted, things that we do without thinking, are things that we have choices about whether we do or not. So international work tends to raise those discussions. And finally, it helps us construct more informed hypotheses about teaching and the effects of teaching. Okay, so why am I talking about TIMS to this audience, to an Achieving the Dream audience? Well, most notably, the students that you get are the product of K-12 education, right? So it's important to know what's happening to these students and what might have created the situation that you now face when you're trying to teach them. So, things that we learned from the TIMS study. Teaching varies more across cultures than within them. So, it's hard sometimes to convey this fact and have people believe you. But if you watch a collection of videos, after a while you get a sense of this pattern of teaching that you see over and over in each culture. That then if a lesson is described to you in a certain way, you can identify, oh, well, that would have been in a Dutch classroom. Right? There are typical patterns of behavior that seem culture-bound, and that there's more variation across those cultures than we see within them. We also discovered from TIMS, in answer to the hypotheses that people were drawing after the first TIMS study, that in fact, there's not one best way to teach. So when we looked at multiple high-achieving countries, what we saw were different patterns of teaching. Right? We don't all have to emulate Japan. And in fact, there are some interesting ways in which Japan and Hong Kong are different from one another. So two countries with very high achievement, both East Asian countries, places where you might expect things to be much more the same. And in some ways, they're quite different. So that raises some interesting questions about what we have to do and what we don't have to do, that we aren't compelled to act like the Japanese teachers. So in very many ways, what we found in the high-achieving countries did not distinguish them from the lower-achieving countries in the study. So when I talk about the lower-achieving countries, sadly, I'm talking about the US, and to some degree also Australia. The other countries that participated in the study, Hong Kong, Japan, the Netherlands, Czech Republic, and Switzerland, are all among the higher-achieving countries in the world. So when we looked at things that would separate the high-achieving countries from the lower-achieving countries, we actually found very few things. What we did find was extraordinarily interesting, and it came in the form of the way math teachers work on problems. So one of the more arduous things that we did through the 568 some odd videotapes that we had is that we marked the beginning and end point of every single math problem in every lesson. And we coded them in one of four ways. The first kind of problem that or one of the types of problems that we saw is what we refer to as answered only. So that's when I, as a teacher, say, so Joni, what did you get for number 7? And Joni says, 3x squared. Thank you. Sally, what did you get for number 8? Right? So all that's shared, the only math, if you can call it that, the only math that's shared is the answer to the problem. And we saw a lot of that in some of the countries. It was very common in the US. There were also problems that were stating concepts. So things that you would recognize more as definitions. So asking students to provide the definition of a disk or a definition of a circle. Those would be stating concepts. Using procedures problems were those problems that called for students to enact a series of procedures to get to a solution. a series of procedures that were known in advance. Like the students, even if they weren't facile with them, they had learned them to some degree already. And then there was another type of problem that was very interesting. It was a kind of problem that asked students to make connections between mathematical ideas and between concepts and perhaps between problems, things that asked them to draw connections between mathematics and within mathematics. So those were the 4 kinds of problems. And here's what we found. So we looked first simply at the kind of problem that was presented to students. And you can see on this graph that it's really only Japan that stands out against the others. So among the other countries, the majority, so between 41 and 84%, middling around 60% of problems, were problems that asked students to use procedures. I actually didn't put stating concepts and answered only questions on here because these were the 2 most dominant kinds of problems. So Japan stands out a little bit, but the rest, it's a pretty consistent pattern, and the US doesn't look different from any high-achieving country, right? So far, we haven't really identified anything different. Now, I've blocked these off so you can't see yet. We then looked at what happened once the teacher and the student started working on the problem. And that's when there were some really interesting transformations. So we looked only at those problems that had the highest potential for having some really interesting discussions about mathematics. So we coded, so what I'm showing here is only those problems that were presented in a way that would ask the students to make connections. And in the high-achieving countries, which are the ones that are now visible, most of those were presented, or were worked on by making connections. In Australia, not so much, right? So in Australia, a good number of those problems were turned into using procedures problems. So the problem might have been presented in a very interesting way, and then the teacher sort of changed the demands, reduced the cognitive demand on the problem, and turned it into something for which students only needed to apply procedures. Any guesses about where the US fell? The fact that you laugh is sad. But any numbers? Any guesses? 3? So you think that, I'm guessing that you think that the green bar is going to be 3. Turns out you are optimistic. In all fairness, that's not a true 0. The National Center for Education Statistics, who paid for this study, would want me to tell you that it rounds to 0. So it's not quite as bleak as it looks, but it looks pretty bleak, right? US teachers presented rich problems. The students heard rich problems, but they didn't have to do rich problems. And that makes their experience in math classes different from what we saw in 8th grade mathematics classrooms in high-achieving countries. And we think that's important. So to give you a sense of what that might look like, in Japan, what they might do if they're in a geometry lesson, and this is actually a lesson that we have, students are presented with a variety of materials, a worksheet with various triangles on it. They're given free rein to do whatever they wish. They can rip them up, they can cut them up, they can get extra copies, they can do whatever they want, but their task is to find a way to calculate the area of any triangle, to use these things that they have as a tool to figure out what the general principle might be, okay? And at the end, students present to the rest of the class the methods that they discovered. That's sort of a typical Japanese pattern. The US pattern you can probably imagine yourself, but I'll show you anyway. So, same kind of idea. They need to find find some generalized rule about triangles. So, as your very helpful teacher, I will provide you with the formula. Here, let me do one. I'll show you how it works. Okay, now I'm going to give you a worksheet, and you can try a bunch more on your own. And when you're done, you can take the second worksheet and you can do some more for homework. Okay? It's a very different experience. My guess is that latter experience kind of sounds familiar to you. Yeah. Yeah. I think when people watch Japanese lessons, it's one of those experiences of violating all of the cultural expectations that we have. And yeah, the first few times you watch Japanese lessons, they look odd. Okay. So what do I want you to know from the TIM study? A few things. We want students to make connections when they're doing math. And changing the curriculum isn't enough. So there were plenty of problems presented in US math classes that asked students to make connections. The curriculum was there, and the teachers used it. But what they did after that changed the intent of the materials. So the curriculum is not enough. We also want you to know that students become socialized into a maladaptive view of what math is and what it means to do math. And I'm going to explain some more of that when I share our findings from the community college work. But they develop this sense of what math is that doesn't match probably what you think math is, does not match what most mathematicians think math is. And that causes some problems. The other thing to think about, there is not a great deal of research that's been done in community college math classrooms that's on teaching. I mean, we have a huge body of research on K-12 education, but not so much in the community colleges. What small amount there is suggests that the kinds of patterns that we see in K-12 education continue through community colleges. So that's a reason to think that what we're finding or what we have found in K-12 is also relevant to a community college audience. Okay, so then we started our community college work. For me personally, and speaking as the person who did these interviews, this was my first foray into work with community colleges because before this project, all of my work had been in K-12. And this was a fascinating way to start. Students are amazing to talk to, and yeah, that was great. So we I interviewed 30 students. They were from a community college in the greater Los Angeles area, and they were drawn equally from arithmetic, pre-algebra, and elementary algebra classes. 10 students from each of those places. And across the 30, they were balanced for males and females. And I met with them one-on-one and did interviews. They were structured interviews. I had a series of math questions I wanted to ask them to do and to talk to me about. And just to give you a sense of the length of those, in general, they were about an hour and 15 minutes each. That was actually the mean. And most of them, in fact, fell at around 75 minutes. So one of the first things that we found came from one of the first questions we asked. And it addresses this idea that students lack a disposition to think when they do math. So we asked, what does it mean to be good at math? What does that mean? And 77% of students gave answers of this type. Math is just all these steps. In math, sometimes you have to just accept that that's the way it is, and there's no reason behind it. I know, disconcerting. I don't think being math has anything to do with reasoning. It's all memorization. So not just thinking that math procedures and concepts are important and reasoning and logic is important, but really saying that the logic and reasoning is not a part of mathematics. I think that's not what we're aiming for. They also hold maladaptive views about how to get better at mathematics. So one of the closing questions of the interview was, what advice would you give to your instructor about how to help you learn math? And this is also, for me, some kind of interesting evidence against the idea that people know what's good for them. There were a couple of dominant themes in the responses that students gave and the kinds of advice they would give to their instructors. First, and more than anything else, present the material more slowly and with more repetition. think that's not what we're aiming for, right? We're talking about those connections that we think are important. But that's not what students think is important. They also want their instructors to break down the procedures into smaller steps, right? So the steps that we've broken them down to aren't small enough. Please just like make every move even smaller. And again, I think that's not how we're hoping that they're going to be thinking about mathematics. What's also interesting is students' actions reflect their conceptions. So we've taught them that procedures are important, right? We've taken all of those, even those really rich problems. So we've presented a whole bunch of problems that call for procedures, and those, in fact, were executed by executing procedures. We also offered them up some rich problems, and instead we turned those into procedures. So from that, they're not dumb. They know that what you think is that procedures are important. We've taught them that procedures are important. So one of the interesting questions, I asked them, place the following fractions on a number line. So 4/5, 5/8, -3/4, and 5/4. We chose those pretty deliberately. Have positive and negative, have some greater than, that are between 0 and 1, some that are more than 1. We have some neat inversion of, yeah, we gave way too much thought to the fractions that we chose. When I asked students to put those numbers on a number line, 30% of them set out first by dividing. How would that help? Okay, so you can compare decimals. Yep. So that's a valid argument. So if you're constructing a number line, it might be helpful if they're all using the same units. Combining fifths and eighths makes for a messy number line. So if you're thinking in advance, as you might have been, you thought, you know what, I'm going to give them a common unit. I'll divide, turn them into decimals, and put the decimals on the number line. Great. If only they had done that. 2/3 of them who started dividing didn't do it to get a decimal. They did it to get another fraction. So 2 things to see there. Number 1, if you couldn't place the first fraction, why do you want a second one? Is there something about that second one that's going to serve you any better? I mean, I don't think so. The other thing is, so they obtained, I wasn't kidding when I said, they obtained a new fraction, a new one, different from the one they started with. So the most common way to do that, in fact, I think, yeah, what I saw happen again and again, which astounded me as I did these interviews, is that students would start with 4/5. They would do something to it. They would divide 4 into 5. They did it backwards, right? They got 1 1/4. I guess that didn't help them. So they kept going and turned that into 5/4. And then they placed the 5/4 on the number line. So they could place a fraction, I won't say correctly, but they could place a fraction on a number line. But they didn't do it until they had the second fraction. And they didn't seem to notice that if you start with 4/5 and you manipulate it and you get 5/4, that there's a problem. Right? No one noticed that that was a problem, which that's a problem. Yeah. Here's another student's response. Same numbers. And what you see in the work to the left is that he took 4/5 and 5/8, and he turned it into 32/40. And I don't need the Wi-Fi. Turned it into 32/40 and 25/40. What did he do? Right, because that's what you do. That's what you do when you're given 2 fractions that have not, unlike denominators. You make them have common denominators, so he did that. And then, interestingly, he placed the numerators only on the number line. We see a lot of student work that reflects this belief among students that a fraction is actually not a single value, but composed of two individual values, the numerator and denominator, that have no relation to each other. So he was one of those students. He placed the numerators only on the number line. And he happened to have some other different thinking, so he placed 32 and 25 on the number line, which were the numerators of the fractions with the like denominators. But then he also placed -3 and 5 on the number line without manipulating those. Of course, they started with, they have a common denominator, right? So there's nothing you need to do to those, right? -3/4 and 5/4, that one's ready to go, okay? But I think what this suggests is that when students get numbers placed before them, they want to act on them, right? They want to throw some procedures at them. Not necessarily any procedures that make sense, and not necessarily that they even had a plan. But they know they need to act on it, and that's what they do. They're very obedient that way, right? We have taught them that procedures are important, and so they do something. Here's another one that we thought we could give them an opportunity to reason without necessarily having to do anything to it. So one of the favorite problems we ask in our lab, and if you come visit our lab, we'll probably ask you, because we ask this of everybody, if you have A/5 and A/8, which is larger? So we asked that of the community college students as well. Many of them struggled with that. But the kinds of thinking that we got when they struggled, yeah, go ahead. Yes, we did. Yeah. I'm not sure that they would have seen that as a restriction. But yes, we did. When they were stuck and we wanted them to continue to do some thinking, I often said, well, would it help to substitute a value for A? And that often, I gave them something to do. And they appreciated that. And they generally chose the number 1 and plugged something in. And this kind student thought, well, that's still not enough work to do, so I'll multiply across and get 1/40. And then I asked, so how is it that helps you decide, or does that help you decide which is larger, A/5 and A/8? And she said, it kind of helps. I mean, with all due respect for these students, they were trying so hard. And they came on their own time to do, these are all developmental math students, they came on their own time to talk to me about math for an hour and 15 minutes. I mean, thank you to them. So I'm not trying to disparage them, or am I trying to disparage their thinking? I actually think their thinking is really interesting, and I think we've done a really good job of creating it. So, I loved this question. So I asked this simply verbally. What would happen if you had a number and you added a third to it? Would it be more than what you started with, less than what you started with, the same as what you started with, or can you not tell? And happily, 87% of students were able to answer that question correctly. That if you add a third to a number, you get something more than what you started with. Fabulous. Next, immediately following that, I asked them a completely unrelated question. I asked, if you had A plus 1/3 equals X, is A more than A, less than A, the same as A, or can you not tell? 30% said you can't tell. Unless you know A or X, because then you know, of course, you know by now, then you can do something. Without that, you can't do anything. Now, that's in spite of the fact that of those 30% who said that question was unanswerable, 78% of them had just told me the answer. They had just answered it when it was expressed without mathematical notation. They can think about these things. They can reason in a way that we call mathematical. But if you put math in front of them, you put notation and symbols in front of them, it stymies them. And they want to do something. Okay. I'll let you take a look at this. When we use the standard algorithm, why do we put a 0 there? I heard something. Thank you. Because you're multiplying by 10, not 1. Right. In fact, this is a really hard question. And in fact, many students don't think there is a reason. They were told to do it, and they do it faithfully. So just to break it down, this algorithm makes perfect sense, right? It's distributive property. So the first partial product is simply 3 times 22, and the second is 10, as we said, 10 times 22. Right? It makes sense. It's not arbitrary at all. Not at all. If you want to break it down further, and sometimes it's actually done with younger students to break down this algorithm even further, sometimes you see it like this. And then again, it's distributive property, right? You might wonder why we think this stuff is important. Well, it's distributive property. It's a notion that carries through a lot of mathematics, right? And another way of writing what that algorithm is this. The quantity 3 plus 10 times the quantity 2 plus 20, right? These students are going into algebra, and they sometimes think that algebra is this completely new set of rules, right? Well, it's a different class, and of course, a different class comes with new rules. And then you throw letters in there, and now it must be a really, not just a new set of rules, but like a completely different set of rules. And they don't see that what they're doing when they're doing FOIL is something they've been doing all along. They've probably been doing since 2nd grade. So those are the kinds of connections that we want students to see. And we think that if they see those connections, math is going to make a whole lot more sense. And they'll see that math does make sense, that math is something that makes sense. So that even if it doesn't make sense to them, they'll find a way for it to make sense. That's something you should be after. So I thought I'd let you hear in the voice of one student. This is what happened when I asked him this question. Oh. I'm not getting... Oh, sorry. You know what? I'm going to start that over because I finally found the volume. So you're programmed to do it, or he's programmed to do it, right? And we heard a lot of that students said, well, all of my teachers have said to do that, so I do that. Okay, so one of the things I'd love for you to take away from this is that students learn the math we teach them. And if we tell them, or if we demonstrate for them in some way that math isn't something to think about, then they'll think that math isn't something to think about. They do come away with this idea that math is instead a collection of procedures that need to be applied. And they apply them faithfully at every opportunity, even when you don't want them to apply the procedures. And they apply the procedures just rotely, right? They apply these memorized procedures without any regard to meaning, and they might think that there is no meaning. One thing beyond this, as students get older and they sit through more and more classes and are given more and more procedures to execute that they see as in no way related or connected to each other, that's an overwhelming burden on your memory. And it's really no wonder that if you think that all of these rules are discrete, that at some point things fall apart. So this is sort of our hypothesis. This is, and this is not something that we have tested yet, but we would like to in our work as we go forward. And And this is what we think happens to students. So young children, so research on young children indicates that they have good number concepts, and these concepts of number are interconnected. So they're good fertile ground to start with. And then we send them to school. And then for years on end, they practice procedures and they memorize rules. So, and then the students sort of break off into different groups based on their response to that. So there are some students who insist that math should make sense, and they will make it make sense with or without the teacher's help. And those students we don't worry about. Those are probably the students that are more likely to enter into STEM professions, right? They're looking for the interconnectedness. There's another body of students who are simply good memorizers. That huge burden of all of those disconnected facts and procedures, they memorize them well. And so they succeed. They pass math classes. They might get all A's in math classes. They don't really get math, but they can give you the right answer. And then there's this body of students who don't memorize well and don't seek out sense between the things that they're taught. And after a while, it's just too much to hold in memory. So you start applying these rules and procedures indiscriminately. And you end up in community college math classes, struggling to have it all make sense. So this is just our hypothesis. You don't have to agree with it. But yeah, this is one of the ways we think about when we're thinking about the students that we're working with. Okay. Some other research. Yeah, question. Yeah, go ahead. Yeah, so they can hold it in working memory for long enough to take the exam. Yeah. Right. I think that's often a problem, which is unfortunate because there are many future exams that will call upon the same information. So James Hebert and Doug Grouse in 2007 did a really fantastic literature review of all of the empirical work done on mathematics education. Really terrific, for me it's like one of the Bibles that I rely on. And they've identified two key features of classroom instruction that promote the kinds of conceptual development that we're after. And when I say that we're after conceptual development, I should say that I also realize that being able to perform procedures and execute these algorithms and all of that is also terribly important. I'm not trying to put conceptual knowledge over procedural skill, but it can't be the procedural skill alone, that we really need to build those concepts in there. So the two key features that they saw across this large body of work that had been done that promote conceptual development are explicit attention to concepts. So that's right in line with what we were finding in TIMS. This idea of making connections among facts, procedures, and ideas. Right? So in fact, the work that we did is completely consistent with the work that James and Doug did. The other thing they found was that students need to struggle. Now, you might think your students struggle enough. We want them to struggle in a specific way. Oop, didn't mean to say that. What we want them to do is spend at least some time grappling with important mathematics, right? To not have everything be spoon-fed. And I like talking about struggle with people because we get a lot of pushback when we talk about struggle. Very, sometimes loud, sometimes unfriendly, pushback. People who are really talking in defense of the students that they're working with. And I have all respect for them. What we're not trying to do is create a painful experience for students, we promise. So I think it's helpful to sort of examine more closely this idea of struggle. And this is the definition that, that James and Doug offer. They are very careful in their language, and I respect them for that. And because of that, I chose to not try to paraphrase, but rather just to draw what they said. So we use the word struggle to mean that students expend effort to make sense of mathematics, to figure something out that is not immediately apparent. Right? We give students a lot of math to do that, for which the next action is immediately apparent if they've been paying attention. We do not use struggle to mean needless frustration or extreme levels of challenge created by nonsensical or overly difficult problems. So if you've studied anything of Vygotsky, what we're talking about here is zone of proximal development. We want tasks to be within students' reach, but something for which they must reach. We also don't mean the feelings of despair that some students can experience when little of the material makes sense. That kind of agony is not what we're after, right? The kind of hair pulling when it's just not within the student's grasp. And the struggle we have in mind comes from solving problems that are within the reach and grappling with key mathematical ideas that are comprehensible but not yet well-formed. And I think that's what we're seeing when we look at Japanese math classrooms. Again, not to say that we need to teach the way that the Japanese do, but we need to somehow create a setting in which students can grapple with mathematics in the way Japanese students do. Okay, there's another body of literature. It's related to this concept of struggle. It comes from cognitive science, and it's the notion of desirable difficulties. So desirable difficulties. Conditions of instruction that make performance improve rapidly often fail to support long-term retention and transfer. Another one of those examples that we don't always know what's best for us. Right? There are learning experiences that we have that make us feel like we're learning a lot, and we're not. But it feels good, right? You feel a sense of competence, but it's a false sense of competence. And it's true also that conditions of instruction that appear to create difficulties for the learner often slow the rate of apparent learning, but they also optimize long-term retention and transfer. So there's an interesting study that was conducted on undergraduates. They were given practice in a variety of ways. So they were asked to practice for a test, and they could either reread the material, they could answer short answer problems, or they could answer multiple choice problems. So they tested their performance after a period of studying, and they also asked students at that point to try to rate how much they had learned from their study experience. So what was found from that is that students thought that the multiple choice practice led to the best learning. What in fact led to the most learning was the short answer practice. That's harder. It's harder, and when you self-assess, you might come away thinking that you're not learning very much because it's hard, right? It's hard to answer, and you might see more errors. But the rates of learning, and also in delayed post-tests, as well as transfer to different tasks, are higher following that kind of activity. Another example of that, blocked versus random practice. So people often study a particular concept and are very focused. They might have even been encouraged to do this. They're focused on a particular task, and they do it, one task after the other, multiple trials, until they feel like they have it. And then they move on to the next concept, and they do multiple trials until they feel like they have it, right? So we refer to that as blocked practice. You could also interleave the practice. So you could practice the first concept for a problem or two, and then the next concept, and go back to the first one, and then back to the next one, right? Bounce back and forth. It's harder, because every time you start at that, if you go back to another concept, whether you've done it before or not, you have to recall all, okay, yeah, when I work on this kind of problem, these are the things I need to be thinking about. And you have to do that over and over again. You can see how that might lead to improved learning, but it's also far more frustrating. And it makes you feel like you're not learning as much. The last example that I put up there, some of the work on desirable difficulties isn't, well, it's not all done in academic settings. They've also done it in sport settings and things. And this particular beanbag study, they had students who were going to take a test on getting a beanbag, hitting a target with a beanbag. And that beanbag was going to be at some distance. So the students were like 8 years old or so. The distance might have been, 5 or 7 feet away. And they gave the students 2 different kinds of practice. In one kind of practice, they asked students to do exactly what it was they were going to be tested on, right? Over and over again, toss your beanbag to a target that's 7 feet away, just over and over again. Right? For the other group of students, they gave them target practice that they never tried 7 feet. They gave target practice at 6 feet and 8 feet, 6 feet and 8 feet, 6 feet and 8 feet. And you can tell already by the way I set this up which group performed better. Yeah, the 6 and the 8. The students, well, not students in this case, the children who never practiced the task on which they were going to be tested, did better at that task than students who had repeatedly practiced that exact thing. Right? The notion being that practicing 6 and 8 and 6 and 8, you develop more of a sense of what goes into producing that particular distance, right? So that when you need to vary it, you have the skills to draw upon to say, okay, well, I need to make it somewhere fall in between there, you get 7. Yeah. So, but again, it's not easy. That's not the easiest way to practice. And we like this idea. That's the kind of struggle we're talking about, that it's not necessarily the easiest thing to do. Okay, and then the last bit of research that I want to share is this notion of deliberate practice. So it comes from the literature on expertise and the development of expertise. Again, it's not just academic expertise. So in fact, they study musicians. They do a lot of work with chess players, also with athletes. And yeah, like I said there, what they found there is that repetitive practice doesn't cut it. That training, the idea behind deliberate practice is that training is designed to focus on improving very particular tasks, and that you increase the variation and complexity over time. And that's very different from what we're doing in our classrooms, certainly in the K-12 classrooms that I see. That's not really the cultural routine that we have. Like, we teach a concept, and then we practice that concept. So that's deliberate practice. Now, so what are the implications of this for improving teaching? So teaching quality is defined by the quality of the learning opportunities they create for students. So what we're really focusing in our work now is these learning opportunities. And we have 3 very particular ones in mind that are based not just on our own work, but are grounded in the larger work in education, more broadly, and in cognitive science. This idea of making explicit connections, that they be explicit. I don't know how many teachers ask students beyond 2nd grade why there's a 0 in that algorithm for multiplication. They might assume students know. Right? And giving them practice with the algorithm doesn't give them any access to the things to which it's connected. So we want teachers to be explicit about the ways what they're doing is connected inextricably to the things they've already done. What we're talking about is changing cultural routines, right? productive struggle is not currently part of our cultural routine in the US, and there's pushback. And deliberate practice, that's also not the way we tend to work on homework and do practice in the latter half of lessons. But we believe, based on all this research, that if teachers can, in some way, we're not here to dictate any particular way, but in some way, if they can create those opportunities, it's those opportunities that will lead to learning. That's what we're arguing for. So, changing cultural routines. It requires first that the routines be brought into awareness, right? That's one of the things with cultural routines. They're implicit. We don't pay attention to them often. They're the things that drive our everyday existence, and we just go about doing them and executing them without thought. So we want to really bring those things into focus, those things that we often don't think about. Some of the work that we're doing is grounded in improvement science, including some of Mike Ruther's work on Toyota Kata, if you're familiar with that. If you aren't, that's a great read, Toyota Kata. So it's about grasping the current condition, right? To have some sense of where we are now. The next step in changing these cultural routines is that we need to figure out where it is we want to go. In Toyota Kata terms, to establish the target condition, right? So we need to know where we are and where we want to be. And I think that's sort of, to this point, where our work has taken us. I think we've done a decent job of establishing where we are in terms of teaching and the student thinking that results from it. We also have some ideas about where we want to go based on successes we found elsewhere. But that's not it. The next step is that we have to make deliberate and incremental changes. And so in Toyota Kata terms, that's to identify and remove obstacles. And oh, there will be obstacles, right? Obstacles from colleagues, obstacles from administration, obstacles from students. Obstacles from students. I have a daughter who's 12 years old. I love doing math with her. She won't let me do math with her anymore because she knows that I keep asking her this question, how did you get that? How did you know, right? That's so annoying, especially when everywhere else in her life, she doesn't have to bother with that stuff. It's so much easier not to bother with that. Right? Yeah, so I don't get to see her work anymore. So we need to improve the learning opportunities available to students. We need to make them struggle and let them know that that's okay, and to support them as they feel the discomfort of treating math as something different as the way they usually think about it. We need to let them struggle, but we need to have them struggle with something that's important, right? To not have them struggle randomly, but to struggle with these connections, something that's important in mathematics. And then we want to have them practice in ways that extend and deepen their knowledge. On a recent homework assignment, not one that I was allowed to help with, but one that I was allowed to see, my daughter shared with me her homework page, and she pointed to me, there were 20 problems on the page, and she pointed to me at the end of the second row, this is where I understood it. And then she pointed at the bottom row, and this is where I hated it, right? She got what she needed to get, but she had to do so much more, more problems beyond that for her served no purpose, really. I'm all about homework, and I'm all about homework that creates learning, but homework that just serves no learning purpose, yeah, that I could totally understand. Yeah, by that time, you hate it. So if we're successful at creating those learning opportunities for students, I think that as a byproduct, or as, alongside that, we're going to change their conception of what math is and what it means to do math. And they'll see the beauty of this domain that is so interconnected in ways you can discover all the time, new ways. But I also want you to know that there's hope. I want to give you one last example. So this is a question I, of course, asked of all the students in the interview project. I actually did the math on this one for them. So I wrote this down, that 462 plus 253 equals 715. I provided that. And then I asked, how would you know if this is right? And most students in the interviews simply did the addition again, right? Double check the addition. That's reasonable, right? That's fine. Of course, I wanted to push them beyond that. So then I asked, well, is there a way you can check it using subtraction? Most of them could do that. They did it in interesting ways. So this particular student subtracted 253 from 715. Again, totally correct, totally viable, all's good. But, and here I want to draw one more connection. This is a student who was in elementary algebra, and if we are asking students like him to understand this notion that if A plus B equals C, then C minus B equals A, and C minus A equals B, right? We want them to know that. But they should know that from some of their basic arithmetic, right? So when the student asked, when the student subtracted 253 from 715, I asked him this. There's a lot in there that I find fabulous. Right? This particular question came about 40 minutes into our interview. And during that 40 minutes, I, being my particularly annoying self, asked every time, so how did you know? How did you get that? What was your thinking? Right? After 40 minutes of working with me, before I even asked on this question, he says, oh, I knew you were going to ask that, so I started to think. 40 minutes, and we had sort of a new routine, right? And he was ready. He sort of had already internalized it. He was ready to take it on. He was already thinking about it. Fantastic, right? And then he gets the answer. He's so excited. I mean, he was so excited. He learned something. He says that too. That's so great that I learned this just now. Now, if I go back to the transcript, I can tell you that the sum total of all of my utterances were something like, you can try it if you want. Right? So in terms of the learning opportunities that were created for him, it wasn't so much that I intervened in any kind of spectacular way. I really didn't. I asked him a really good question, and I let him try it. And when he wasn't sure, I let him experiment with it. And he made this really cool discovery that he's going to go share it with his teacher. That's so great. I mean, I'm not sure what his teacher thought when he went to go share that, miraculous finding. I hope the teacher shared his enthusiasm. But it does tell me that, if we can establish in such, or if, we can do this, right? We can work with students and get them thinking, and they're completely capable of thinking, right? And they're really excited when they do. So, thanks. I know that we have a session until 5, so I think we can open up to questions.
When you were looking at the international studies, how much did you think about how much time do these cultures spend on fractions? Because being on the system we are with feet, et cetera, we need fractions a lot more. And I'm wondering, for the countries that are on the metric system, do they spend as much time as we do teaching fractions and all the things associated with fractions?
Our study was not a curriculum study. And so, in fact, there was a curriculum study done entirely separate from us as a part of TIMS. So I can't speak, I'm afraid I can't speak to that in particular. Yeah. It's interesting to think how that might be related, and it'd be really interesting to look at the relations between that and metric and English unit measures. And I just don't know.
Thank you for your talk. I had a question, kind of lengthy. Many, many years ago, probably 20 years or so, there was a study done that indicated, it was by National Council of Teachers of Mathematics, I believe, that indicated that the higher degree in mathematics a person had, the less likely they were to use certain kinds of classroom activities that the National Council of Teachers of Mathematics thought would be helpful for students to learning, making connections, things, things like this, okay? The data you presented at the beginning kind of flies in the face of that, because as a department chair at a community college, I mean, I can count on one hand the number of people who have come into my office applying to be an adjunct instructor and have, given me the correct answer to, if a student does this, what did they do wrong? And the answer to that question was, they violated order of operations. I mean, they dance around the issue. They say, well, they were supposed to do this first, but they did the other thing first. Or it just seems to me that we have to somehow raise the bar on where the level of thinking of the instructor is if we ever want to raise the bar for the level of thinking on the part of the student. So has there been any more recent study done in that regard, and make me aware of it if it's been done?
To my knowledge, there's no further work that indicates an inverse relationship between amount of math knowledge and effective use of use of effective pedagogical strategies. I don't know of something like that, but I do know that one of the very current conversations in education is about pedagogical content knowledge, right? So to have content knowledge in the field, so you might have a high degree of content knowledge of mathematics and still lack pedagogical content knowledge, the knowledge about common misconceptions, common errors and what they might indicate, and to know the most appropriate interventions to follow up on those misconceptions. So I don't know that there's an inverse relationship. In fact, I would suspect there's not an inverse relationship between content knowledge and pedagogical content knowledge. But if you really want good teaching, then pedagogical content knowledge really needs to be there too. There's Deborah Ball does a lot of at Michigan does a lot of work on PCK. Yeah. Did that answer your question? Part of the answer to your question is I don't know of any more recent research on that connection. Rounds to zero, but yeah.
If some of the instructors who were observed actually understood the connections that they should have been making. So I don't think we're off the hook here.
Right, so understanding the connections is a big deal, right? Especially, I mean, we are all a product, or We are all a product of K-12 education somewhere, and if we are a product of K-12 education here in the US, we are a product of an environment in which those connections were not made. And we don't necessarily know where they are. Right, so if we as instructors don't know where they are, or the instructors in the classrooms that we videotape, if they don't know where they are, then there's no hope of pointing them out to students. Yeah, we're definitely not off the hook. Yeah.
My question is related, but it comes from the K through 12 world, where I know the studies show that the more math anxiety the teacher feels, the more that is transmitted to the student in a big way, and so you see a real decline in their math ability because of the anxiety of the instructor. What I wondered is, did you look at that in other countries about the level of math anxiety with regard to the teacher and its effect on the students?
We did not look at math anxiety. We actually did not look at, in the video study, we really didn't look at any psychosocial variables like that. But that is a fascinating one. And Sion Bilak, who is at University of Chicago, has done a lot of work in that area. And indeed, teachers who have math anxiety transmit that math anxiety to their students. And female teachers who have math anxiety transmit that anxiety in particular to the females in the classroom. Sometimes the males are immune, but yeah, there's a huge body of research on that and growing body and really interesting, but we didn't take that into account at all in TIMS.
I was wondering if you could comment kind of on some of the reform movements within community colleges at this point to do better than we're doing. And I mean, this will be a crass oversimplification, but it seems to me that we've got, we've had such failure with the faculty members standing at the front of the room, doing the problem for the students and finding the answer and then giving them homework, that we've now moved to a lot of these emporium individualized learning modules and hybrid modules and using the My Math Lab and other variants which rely enormously on the individual student brushing up on what they should have known before. But none of those, to me, seem to do what you're talking about here. I mean, the engaging the concept, the productive struggle, I mean, it seems like it's just trying to accelerate the old way of having memorized these formulas, in a sense. And I mean, some of the things that the Carnegie work does seem to me to be one of the few things doing what you're talking about. So, I mean, because, I mean, 40% of the programs that are here for the ATD conference are on developmental math, and yet they have dramatically different assumptions undergirding them about what we can do for our students to improve their success. So I'm wondering if you could just maybe comment on what's going out there to try to improve student learning.
First, I'm not surprised that there's so much here on developmental math because it's a huge problem, and it's a huge problem that needs that much attention. In terms of the different ways of approaching it, I don't think that ours is the only approach that's important. I do think that all of the other variables, the addressing out of class, burdens on students, addressing their anxiety, any host of other variables you can look at, I think are also incredibly important, and I don't want to dismiss any of those in the least. When it comes to programs that talk about instruction, when we're talking about classroom instruction, I really, really think that where the research is pointing us is, yeah, these three variables that I hopefully said enough times that you'll remember, the productive struggle, explicit connections, and then I paid a little attention also to deliberate practice. I really think that the research points us in that direction. It might not be the only successful direction in which to go, but I think if you are inconsistent with those things, I'd be skeptical. That's my opinion.
So I'm wondering, first of all, thank you so much for giving us all that wonderful body of research that we've heard from Carnegie before, some of it. But this last piece I think was really wonderful. But I'm wondering, what are universities doing, and what might community colleges just do to their teacher preparation programs so that teachers leave our two-year schools and go on to the four-year schools better prepared to do these kinds of things? It seems like the curriculum that we're using in our programs has not changed.
Yeah, so Lucy, what population are you thinking of? The teacher prep programs? So what teacher prep programs on university campuses are doing? There is so much to be done, right? And if you are a student in a teacher prep program, you might get one methods course that covers math and science for all grades, right? And that's it. I mean, I feel like I've been studying math education since, I don't know, almost 20 years. And I feel like I'm almost ready to go into a classroom. It's hard, and to do it well, there's so much to know. I honestly don't know what the solution is to that, because there is just so much I would want people to know when they come out of a teacher prep program that there really is not time to do. Well, if we take UCLA as a very specific example, you know, Megan Franke is head of the teacher ed program there, and her own personal research is in math education and contributes to this body of knowledge. So she is incredibly well versed in the research in the field. But the inertia is intense. You know, it's changing huge systems. You can talk to Bernadine about everything that needs to be changed if you want to change a course. There are so many forces fighting against it. So I don't know. That's why I do research.
Yeah. First, as a former high school math teacher, I can tell you that teaching at the community college is very much like teaching 6 through 12 at the very least. And I have two questions. It was asked before by somebody about math anxiety at the elementary school level based on the teacher's math anxiety. And how much have you found that some of these deficiencies that you presented with the graph, with the 0, are due to, say, the second half elementary school level, 3 through 5, 3 through 6, where teachers don't have that expertise, that they're trained in general elementary education? They may not be very fond of math. They don't have that training, and they foster this idea of this is how you do it, just do it and move on.
Yeah. As
opposed to changing the concepts teaching the concepts and how that relates to the rest of the world with those higher performing countries. And secondly, to use a somewhat famous quotation if you're a science fiction person, how do we get the students to unlearn what they have learned? That it's simply a rote procedure, and what tips, what techniques do we have that you have used to get them to think about these things?
So I'll address your second question first. We talk about that second part a lot, like what would we do to undo what's been done to students? And I think what we're toying with, and we don't yet have a grant to execute, is developing a course where the first half of the course, there are no procedures to execute, right? That you pose questions that you must think through without pen to paper, and that you must reason through to try to break students' habit of executing procedures every chance that they can. And our thinking being that if they can do that, we can break the habit, and we can also get them to see that math is more than executing procedures, and we can build their confidence in knowing that they can think things through and get to an answer. And that often thinking things through is, you know, you don't have to go through all the procedures. There are lots of times that you can just reason through a problem. So if we can get them to see that first before we ask them to do anything. But I don't know of any program that's like that, that is so focused on reasoning. But I think that would be an approach that I'd like to see. Your first question was about math anxiety and whether
The level of, say, for lack of a better term, mathematics training of the second half of primary education in the U.S. compared to the rest of the world of the countries that you showed.
Yeah. Much of the research on math anxiety is done in a lab setting, so there hasn't been as much field work, and I think that what you're describing would need to be something investigated.
Not so much anxiety, simply
The training.
the training of the teachers. That, like you
Content
said,
training.
You know, they'll take elementary ed, they'll take one class on how to teach math.
Right.
And that's it. How does that compare to the countries that are performing better and are getting a little better results?
It is true that in some high-achieving countries, you're required to have at least a master's degree in the subject matter knowledge. At least if we're talking 8th grade and 7th, 8th, secondary school, that you have to have a master's. So that's certainly a level of training that exceeds what's required here. The problem is that, yeah, a study like that is just a little more difficult to do because there's kind of a narrow range in the U.S. of preparation. The people that we send out into our elementary schools have generally pretty, training that falls within a narrow range. And if there's not a lot of variability, then it's also something that's hard to test. Yeah, I'm not saying it's not important. I do think it is. Yeah.
Hello? Hi. So just, I'll take a minute before I ask the question. So my son is in the 4th grade, and last year they were doing that extended distribution. You showed that. So yesterday I asked him, he was doing multiplication. I asked him, why do you put 1 0? Why do you put 2 zeros? Because it's tens and this is hundreds place. The place values are different.
Awesome.
One of my classes, it's a pre-algebra class at one of the local colleges, started on Monday. And I was doing the same multiplication. And I asked, there were 37 plus few people to add. I asked them, why do we put zeros in there? Nobody knows. So how is that possible that elementary school students, and I asked today, I went there in the morning to my son was there for a few other kids, his friends, and I asked them, guys, do you know how to do all this? They understand why they have to put 0, 1, or 2, or 3. Depends on the place value. And how is that possible that they do that? And high school graduates don't know how to do that. That's the first thing. And the second thing, I teach community college. I try to teach at university, graduate level classes, and I don't know if, in California we have class, it is math for elementary school teachers, and there's another class, it's called geometry for middle school teachers. That's a graduate level class, you teach that at the universities, not at the 4-year colleges. I mean, not the 2-year, but 4-year colleges. Anyway, so I was teaching that for 2 consecutive quarters, and after that I had to leave the school I was in, no names. So because out of my 35 students for the first quarter, 2 people passed. Out of 35 on second quarter, 3 people passed. Why? Because for the second midterm quiz, I give them timetables. You know, guys, the second grade, when they do timetables, they have 100 problems on a piece of paper, and the numbers are from 1 to 9. I mean, if you have been at school, you have to know that. Okay, so out of 35 people, only 2 completed that. My daughter, she was in second grade, was doing that in 46 seconds. My son is doing that in 51 seconds. I just tried. These people, I give them 5 minutes. They are going to be geometry teachers in middle school. Okay, so I had a few different conversations with the dean and the VP and all that. I had to leave. I said, guys, I'm sorry, but if these are going to teach my son, no. Thank you. So I understand that it's good to save a forest 1 tree at a time and all that, blah, blah, blah. Okay. So what do we do?
I think, yeah. So let's see if I can stall for 20. I think part of it is, a great start is doing what you did, right? Demanding something more. But you had, then you have to hope that that's worth it. Yeah, I mean, I took when I was an undergrad, I thought I was going to be an elementary school teacher. And I took those classes that you just described. And I was pretty disappointed. I was an undergrad at UCLA, and I was pretty disappointed with my classmates. I think they could have done the times tables, but it definitely was not. I was surprised at the level of math understanding among these students, and they were UCLA undergrads, destined to be teachers. I'm excited by programs like Teach for America. So programs that really attract kids with enthusiasm, with good, solid content knowledge, and then helps them to be better teachers. And the teachers that I've seen in classrooms who've come through that program, my experience is I see them do a really nice job. So I think we need to attract people like that into the profession, and not just through small scale or relatively small scale programs like Teach for America, right? We need to get those, we need those people in classrooms. With respect to your first question, I'm now done trying to avoid the second one. Your first question is, how is it that your son can know that in 4th grade, but the community college students don't? I think part of that is the fault of, students need a reminder. And if you're talking, the one really nice thing about making connections is it gives you this forum for making reminders. Even to things that are really simple. Like, we talk a lot to students about things like, what does the equal sign mean? Right? So we have conversations about things that sometimes teachers think are too obvious to talk about. And so I think you just need to keep bringing these ideas back. And for, not necessarily the times tables, I think that's a different issue, but I think there are a lot of concepts that kids get when they're younger, and they're just never, they never come up again. And so, yeah, so they forget them. Yeah.
I don't teach math, I teach reading, and students that I teach with somebody else. And so I'm looking at this a different way. I had one question: what does the classroom management? What are the conditions in the classroom when they're doing productive struggle? Are they well behaved? Because I can see that being a problem. And I've taught middle school. I've taught high school. What's the classroom like in Japan when they're productively struggling?
Oh, I thought you were talking in the U.S. when they're productive. I can speak to actually both.
Oh, I didn't think we did that.
Well, as part of another study that we're working on, Finland has come up in international tests in recent years as like #1 or #2 in the world. So most of the other countries near that position, I promise I am getting to your question. Other countries in that position are often East Asian countries. So Finland is this anomaly. So there are a lot of educators who are trying to understand what's going on in Finland, especially educators in other Scandinavian countries, because their attitude is like, what are they? Why are we not? What? So we're working on this project right now between Finland, Norway, Sweden, and the U.S. And across those countries, we've videotaped the introduction to algebra, variables, expressions, and equations, for a week in 4 classrooms in each of those countries. So we're just in the midst of starting to look at that data. We collected 4 days of them working on what they would have been doing usually, just without our presence. And on the 5th day, in all of the classrooms in all of the 4 countries, we gave them a set of rich problems to work on, problems that would elicit struggle. So, so I got to see in at least the 4 US classrooms, so there are 2 6th and 2 7th grade classrooms, working on these really content-rich problems that we asked students to let the students work together. And some of the, well, we have some pretty enlightened teachers who we're working with. We're grateful for that. But they let them do it, not really confident that anything good was going to come out of it. And it was pretty amazing. These students, it was near the beginning of the year, but they had never worked in groups on a task, and they were so engaged. And they were thinking and sharing ideas, and yeah, the class is not completely quiet, of course, because there are people talking and sharing ideas. But what I've seen, even in U.S. classrooms, even without any kind of prompting, some really exciting student thinking. I think students are eager. Students are eager to do something interesting. I mean, just like any of us. So if you give them something interesting to do, they do it. Yeah. That's good.
Well, I too want to thank you for your talk today. You've given me some new vocabulary for some old concepts that I've struggled with. The cultural acceptance that it's okay not to be good in math, I think, is one that we all recognize, and now I can call that a maladaptive view of math.
That's a maladaptive view of yourself.
Yeah, that's true. I wanted to comment, too, on the struggle, the productive struggle idea. There was a psychological study probably 30 years ago on traits of people in different professions, and mathematicians were identified. There was a unique spike in the data because mathematicians have a higher tolerance of ambiguity. And by that, they meant when you're given a problem that looks impossible, mathematicians are the ones who will say, well, that's interesting, and other people get frustrated and quit. And so I'm wondering how, in developing strategies to help our students with productive struggle, what techniques do we have to encourage them and engage them past that point of frustration?
First, I want to make a comment that's a really interesting finding about tolerance for ambiguity and among mathematicians, and it makes me wonder which came first. Do people who are tolerant of ambiguity, do they become mathematicians, or or if working through math in some successful way leads you to become more tolerant of ambiguity? Yeah, I don't know. Does anyone in the room do Sudoku? Or any? I think there's something about, we seek out tasks that are challenging, puzzles that we don't have to solve. And somehow we find some reward in getting through it and completing it. Even though we have a bunch of, the product is not very exciting looking, but somehow knowing that, you filled every square, it feels good. It's satisfying. I think if you have some small struggle experiences that lead to positive outcomes, you get to see that those positive outcomes is really satisfying, and that's really attractive, right? Then I think you start to think, I can do that, and it feels pretty good if I've done it. And yeah, I understand that it might not feel so good along the way, but that effort is worth the reward at the end. So I think starting small with some, not huge challenges, but things that lead to success is a good way to start.
Hi, I'm Nicole Gray. I work at the Carnegie Foundation, and I'm also a faculty member at Foothill College, and we're sort of coming to a close of our time here. But before we ended, I wanted to make sure that you know that there are handouts in the back of the room. One of them has information about the 2 Pathways programs that Carnegie has created that help to integrate these ideas that Karen has talked to us today about into the curriculum materials for developmental math students. And then there's another handout that's a flyer for our summer Pathways Forum so that you can have some information about that as well. And then the last thing is that there is a reception tonight that Carnegie is hosting, and you're all invited to attend that. It's from 6 to 7 p.m. in Avalon, which is downstairs on the first floor. And I think we maybe have time for one more question, Karen, if there is one.
we have not explored this breakdown. This is completely hypothetical. And so I can't tell you the numbers in each path. Right now, I would love to just confirm that the paths exist, that we've described something that matches the real world. And then I think we can get to something more concrete on numbers.
I'm afraid that it is probably almost zero, not zero, almost zero.
Round.
Maybe another 5-6%, maybe 3, I don't know, in the middle, and the rest is right there. That's why I want to know if there's a research.
Not yet. I'll get back to you.
Thanks so much, Karen.
Great. Thank you.